Probability. So type 6 in probability is conditional probability, and this is where the second event is dependent on the first. So in other words, this is going to be when something is not replaced. So it's important to note for these questions that when it says in a question something is taken at random, that implies that it is not replaced. If something is replaced, it is generally clearly stated in the question. And it's always important to remember that obviously days of the week, months are obviously replaced because these are fixed items. So for conditional probability, we say that the probability of A, given that B has already occurred, can be found by getting the probability of A and B occurring over the probability of B occurring. So it's important to note that this A line B is our conditional probability, not to be confused with the probability of A less B. We need to know this off by heart. It is not in our maths tables, so it's something that we have to make a mental note of. And we can be given these questions in various different ways. So the first example we're going to look at is including Venn diagrams, where we're given the numbers and we're literally going to complete our Venn diagram and then use the Venn diagram and the formula to find our answer. So here we have X and Y are two events. So I'm going to call the first Venn diagram X and the second one Y. I'm told the probability of X is 0.2 and the probability of Y is 0.25 and the probability of X intersection Y is 0.1. So whenever we're starting a Venn diagram, the easiest place to start is by looking at the intersection. So what do they have in common? So we can see that X intersection Y is equal to 0.1. So therefore, if the probability of X is 0.2, well, let me circle that in red. All of this circle represents 0.2. So therefore, if the intersection is already 0.1, well then the remaining part, this bit here that I've shaded in red, has to be 0.2 minus 0.1. So therefore, if I remove that shading, what we now have is 0.1 and 0.1. And we do the same then for Y. Well, Y, if I circle, in total is 0.25. So therefore, if the intersection is 0.1, then the remaining bit of Y has to be 0.25 minus the intersection of 0.1, which obviously leaves us with 0.15. So let me get rid of all of that. And then we'll fill in what we know. So that must be 0.15. Now, of course, all of this is given to us in decimal form, so we need to check, do they add up to give us a total? So the total number in probability is always going to be 1. And we can see that we have 0.1 plus 0.1 plus 0.15 is 0.35. So, of course, then the remainder must be what is left. So the rest of the universal set, all of that must be 1 minus 0.1 plus 0.1 plus 0.15. In other words, 1 minus 0.35, which gives us 0.65. So therefore we place 0.65 anywhere outside of X and Y. So now if we look at the questions, we're looking at what is the probability of X union Y. So probability of X union Y then is going to be everything inside X and Y. So if I look at that on my Venn diagram, it's all of these. So therefore we have 0.1 plus 0.1 plus 0.15. And therefore that gives us a probability of 0.35. So for part 2, if we're looking for the probability of X, given that Y has already happened, well, that means I need to find the probability of X intersection Y over the probability of Y. So X intersection Y is 0.1 over the probability of Y is 0.25. And 0.1 divided by 0.25 is 0.4. And the last one there then is the probability of Y given X. So it might look like the same question, but it's actually the probability of y intersection x over the probability of x. So y intersection x is 0.1, and the probability of x is given to us as 0.2, and 0.1 divided by 0.2 is 0.5. So it's important to note here that the probability of x given y is not equal to the probability of y given x. So not to have that misconception that they are the same thing. The order is essential. Okay, so this one's a little bit more complex. We've got 3 Venn diagrams this time. So we have A, B, and C. And we have to find these unknown values of x, which is here in the intersection, and y, which is outside of the 3 sets A, B, and C. Now we're told that the probability of A is 0.3. So if I circle the set A, that means that everything inside there is 0.3. So therefore I can see that we have to find x. So that means that 0.3 must equal 0.09 plus 0.04 plus x plus 0.07. So if we get x on its own, what I have is 0.3 minus 0.09 plus 0.04 plus 0.07. And therefore that gives me a value for x to be 0.1. So I can put that into my Venn diagram then. So that's 0.1. And if I shade out the x, and now I can find y, because everything in probability always amounts to 1. So therefore, if I want to find y itself, it must be 1 minus everything else. So that's 0.09, 0.07, plus 0.004, plus 0.1, plus 0.04, plus 0.16, plus 0.3. And therefore that gives me the value for y to be 0.2. Okay, so now we have y. I'm going to shade out the y and fill in the correct number then. So that's going to be 0.2. So now for the second part, I need to find the probability of B given C and C given B. So the probability of B given C is already the probability of B intersection C over the probability of C. So B intersection C, if we shade it, is going to be the overlap between B and C. So that's 0.26. And over the probability of C, well, probability of C is everything there. So that's going to be 0.1 plus 0.16 plus 0.3 plus 0.04. And therefore that gives me 0.6. And therefore the probability of B given C is 0.26 divided by 0.6, which gives us 0.433. So if we get C intersection, or C given B, over the probability of B, so we know 0.26 is still the same intersection. And then this time, if I get rid of that circle, so this time we're looking for the probability of B. So B is everything inside here. So that gives us 0.07 plus 0.1 plus 0.16 plus 0.04. And that gives us 0.37. So 0.26 divided by 0.37 gives us 0.7027. Or if I round to 3 places there. And again, we haven't been told in this question how many places to round to. In an exam situation, we more than likely would be. And again, it's important to note we can see that these two answers are not the same. Okay, so the third one then is the probability of B given that A union C has occurred. So therefore that means we have to get the probability of B intersection A union C all over the probability of A union C. So as we have more things happening, it becomes a little bit more complex. So first thing we want to do is look at the intersection of B with A union C. So if I circle what is A union C, I can see it's all of this. So everything in red there is A union C. And then we have to find, well, what is in common there with B? So if I just shade in what is common in B in yellow there, well, everything in B that's also in A union C is only these three numbers here. So 0.07, 0.1 and 0.16. So therefore that gives us 0.07 plus 0.1 is 0.17. So 0.17 plus 0.16 is 0.33. And then that has to be over A union C. So everything in red there, A union C gives us. So then 0.33 divided by 0.76 gives us 0.434. Okay, so the next one then is find A intersection C, given that A union B union C has already occurred. So therefore that's going to be the probability of A intersection C intersection A union B union C all over the probability of A union B union C. Okay, so A union B union C is all three sets, so everything inside the red there, and we need to find what does that have in common with A intersection C. So if I mark A intersection C in yellow, we can see that we only have 0.1 and 0.04, and all of that is in common with A union B union C. So therefore it's literally just 0.14 over A union B union C, and A union B union C is everything inside of the red there, and therefore that gives us a total of 0.8, and therefore 0.14 divided by 0.8 is 0.175. So the last one then is the probability of A less B given that A union B has already occurred. So therefore that's going to be the probability of A less B intersection A union B all over the probability of A union B. Okay, so A less B, let's go back to our diagram. So everything in A that's not in B is 0.09 and 0.04. And then A union B, well, if I mark that in yellow, A union B is everything inside the yellow. So therefore the intersection of that has to be the 0.09 and the 0.04, which is 0.14. No, sorry, 0.13 I should say. And then over A union B, well, A union B is everything in the yellow there, which is 0.5. And therefore 0.13 divided by 0.5 is 0.26. So always marking on your Venn diagrams, as I have done, makes it a lot easier to figure out exactly what it is that you're looking for. Okay, so let's look at one more example. So here we have in a certain county, 70% of the population live in a townland and 30% live in a rural area. 50% of the townlanders listen to the local radio, whereas only 20% of the rural dwellers listen to the local radio. A person from the county is picked at random, and we've defined the probability that the person is a townlander, given that the person listens to the local radio station. So when it comes to these kind of questions, it can often be quite difficult to decipher what to do with the information. So writing out a little sample space makes it a little bit easier to see how to figure out our answer. So we have two types of people. We have townlanders and we have rural. So we're going to say townland and rural. And then of those people, some of them are going to listen to the radio and some do not listen to the radio. So if we start with the townlanders, we can see that 70% of the population live in a townland. So that means that the total townland is going to be 70%, which is 0.7. And 30% live in the rural area, so therefore we have 0.3. And again, as we said before, with probability, it's always important to check, do our totals amount to 1? If they don't, you've done something wrong. You need to go back and check. So then we can see that we have 20% of the rural dwellers listen to the local radio. So therefore, if we get 20% of 0.3, then we end up with 0.06. So we have 0.06 of rural people are listening to the radio. And therefore, to find out how many of them are not listening to the radio, well, I simply subtract. So 0.3 minus 0.06 gives me 0.24. So therefore, the probability of people not listening to the radio is 0.24. Then if we look, what we can do is see how many of them are listening to the radio in the townlanders, and we can see that it's 50% of townlanders are listening to the local radio. So 50% of 0.7 is obviously going to be 0.35. So therefore 0.35 are listening to the local radio in the townlanders, and obviously 0.35 are not listening to the radio. So again, I can check my totals and I can say, well, 0.35 plus 0.06 must give me 0.41. So we have a total percentage listening to the radio is 41%. And then if I take that away from 1, well, I should get the same as adding 0.35 and 0.24, which is, of course, 0.59. And 0.41 and 0.59 also gives me 1. So 59% are not listening to the radio, 41% are listening to the radio. So what we have to do now is find the probability that the person is a townlander, given that they listen to the radio. So if I say T for townlander, given that they listen to the radio, so or for listening to the radio, is the probability that they are a townlander and listen to the local radio over the probability that they listen to the radio. So townlander and listens to the radio is 0.35 if I look at my table. Over the probability that they listen to the radio, well, my total percentage listening to the radio is 0.41. So therefore, the probability that the person selected is a townlander, given that they listen to the radio, is 0.8537. So there's a really nice question on page 71 in your books, which is question 19. So what you're going to do is go to page 70 and do questions 4, 5, 6, 9, 10, 13, 14, 15, 18 and 19. You're going to pause the video and then you're going to come back and I'm going to have 19 done as a worked out solution for you. Okay, so we're going to unpause the video and we're going to look at the solution for 19. Hopefully there wasn't too much problems with it. And if we look at the question, we're talking about enzyme immunocy tests. And these are going to screen for the presence of HIV. And we're told that 0.3% of the population has HIV. And if a person has HIV, then the EIA test will give a positive result 99.85% of the time. However, if the person does not have HIV, then the EIA test gives a positive result 0.6% of the time. And these are often called false positive tests. So it is falsely testing somebody positive. We're told that Sarah goes for a test. She tests positive, and we have to find to the nearest percent the probability that she actually has HIV. So just like in the Townlander example we just did, we're going to make out a sample space table to allow us to fill in all of the information given to us. Okay, so we want to fill out our table, and we're going to write it in decimal form, not percentage form, just to make it easier. So we have 0.3% of the population has HIV. So as a decimal, that's going to be 0.003. So my total HIV is 0.003. And therefore, if I subtract from 1, the number that do not have HIV is going to be 0.997. So in other words, 99.7% of the population do not have HIV. And again, if I total those two together, I will get 1. If a person has HIV, then the EIA test will give a positive result 99.85% of the time. So in other words, if I get 99.85% of 0.003, then that gives me 0.0029955. So therefore, if I subtract from 0.003, then what I end up with is a lot of zeros, so 0.00000045. And again, just double checking, add those two together, make sure you have 0.03. And then we're told that if a person does not have HIV, they'll test positive 0.6% of the time. So in other words, 0.6% of 0.997 gives us 0.005982. So that's if they're testing positive, but they don't actually have HIV. So then if I subtract that from 0.997, I get 0.005982, take it away, and I'm left with 0.991018. Okay, so if I total everything across then, I have 0.0089775 and 0.991025. And again, if I check, do those two add to give me 1? And they do. Okay, so now if I look at the question, what does it ask me to do? Well, it's asked me to find the probability that she has HIV given that she tests positive. So if I say H is that she has HIV, and P is a positive test. So I need to find the probability that she has HIV and tests positive over the fact that the probability that she tests positive. So has HIV and tests positive is 0.0029955 over the probability that she tests positive. So test positive, if we go across here, our total is 0.0089775. And therefore that gives me a probability of 0.333667502. So what does this actually mean? It means then, well, it means that the probability that Sarah has HIV, given that she tests positive, is 33%, remembering that we have to do it correct to the nearest percentage. Okay.